Okay, hello. So I would like to recap what we did today. Today we essentially looked at the definition of global and local extrema. I want to highlight that our definitions came from Stewart. So a lot of people are familiar with Stewart. Stewart is the author of a really famous calculus book. He's got several different calculus books. Stewart died either last year or the year before. So, calculus books, he's got several different lines of them. And I used the definitions that I used today came from Stewart. Okay. So I want to point out that if you use different definitions, then you classify your extrema differently. Now, everyone pretty much has the same definition for global extrema, right? So a global max, global min, that is not that's not ambiguous. However, when it comes to describing local extrema, so depending on the context, you might have a picture. Let's see here. You might have a picture. Say you've got a picture for your domain, right? So say it's like this, right? So here's A, and here's B. Now, do you consider f of A to be a local max, depending on the text? Some would say yes, it's a local max. Others would say no, it's not a local max because we're not defined to the right, right? There's no definition here to the right. For this course, not a big deal in terms of do you want to call that a global or do you want to call it a local max, yes or no? Because this is a global max, right? So here's what we'll be focusing on in the course. So we've got our current goal, which is what we're going to be working on today, is focusing on finding global extrema. So that's global max, global min, right? Global max, global min. And in a few weeks, we're going to focus on finding local extrema. And so here we will have second derivative tests. Second derivative tests. And these second derivative tests will allow us to determine if uh, if a point is a local max or a local min. Okay, so our current goal is to work with global extrema. So what have we learned so far? So far we've learned that, and from what we did today in class, some functions have extrema and some functions don't, right? This may seem pretty basic, but ask yourself, what's an example of a function that does not have extrema? Let me draw a picture for you, right? So here's an example of a function that doesn't have extrema. Think of f of x equals inverse tangent of x, right? And the domain is negative infinity to infinity. So the graph looks something like this. Now we have our limit, right? The limit as x approaches negative infinity is going to be negative pi over 2. And the limit as x approaches infinity is pi over 2. However, this function does not have any extrema, global or local. Okay, some functions do have extrema. So here we have a theorem. It's called the extreme value theorem. And guess what it does? It tells you some conditions under which a function has extrema. So here's the statement of it. If f, so f is our function, if f is continuous and the domain is a closed interval, all of this needs to be highlighted. So you need for f to be continuous and its domain is a closed interval, then f attains an absolute max value and an absolute min value on AB. Okay. So think about that. Let's answer this true false. If you have an extreme maximum value, can it occur more than once? So are you thinking about this? if you suppose you have an extreme maximum value, can it occur more than once? The answer is going to be true. Why? Let me give you an example. Maybe we can sketch one here. Suppose you have a curve, and here's what your curve looks like. Just plain old, sine or cosine, right? F of x equals sine x. What is the extreme maximum value? Extreme maximum value is going to be 1. Does it occur more than once? Yes, it occurs infinitely many times. It's occurring here, right? It occurs at this point. This is where it occurs. This is where it occurs, right? This is where it occurs. So, true. Yes. Now, here's a question. Another true-false question. There can be more than one extreme value. This is false. There can only be one extreme value, right? Because if you say that you have 2 extreme values, say if you were to say, oh, we've got 2 extreme maximum values. No, you don't. This is the extreme or global. Remember, extreme is the same as global. Global max. This one is not global max because you've got a higher value, right? Over here, right? Because that one is higher. So the point of these, and I think I actually kind of did this out of order, but the point of these 2 questions is to emphasize the distinction between where the global max occurs versus the global max, or i.e. the global max value, right? So the global max value, this is the same as the output. Okay, so this is the output. Over here, where it occurs, this is the input, right? So what is the input where you attain your global max? So I wanted to highlight that. Back to this extreme value theorem. So the extreme value theorem is going to give us conditions under which we are guaranteed to have, for our function to attain an absolute max value and an absolute min value. And here are the requirements. Your function needs to be continuous, and it needs to be defined on a closed interval. So now let me give you, let's do a little page below. I would like to do an example. Why? So here's the question. Why must the function f be continuous? Right? In order to guarantee that f attains global max min. So here's a counterexample. What I need to give an example of a function that is not continuous, f is defined on closed interval, f does not attain global max or global min. Here's my example. 0, 1. So I'm going to let this be A and 1 be B. Here's my function. My function is not going to be continuous. So this function does not attain there is no global max. So imagine this point here is 2, right? Now, if f were continuous, then f of 1/2 would be equal to 2, right? But f is not continuous. So there's no point that is set to 2. And you might say, oh, well, what about
It's 20 hours.
You might say, what about 1.9? And if we look closely, 1.9, will that work? Nope. Because, do you see? F has some values that are higher than 1.9. What about 1.99? Will that work? Nope, because f is still going to have some values that are higher than 1.99. So here's an example where f is not continuous. Since f is not continuous, f is not going to attain the global max. You can't be guaranteed. Now, just because f is not continuous doesn't mean that it won't attain its global max. Here's another example. This is an example of a function where f is not continuous, but it does attain its global max. So what if we were to go up to here and then come down like this, and then here we go. This is a function that's not continuous, but it does attain global max. Right? So what I'm trying to say, what I'm trying to explain is that the theorem, our theorem, which is the extreme value theorem, says if you're continuous and you're defined on a closed interval, then you must attain your absolute max or min. If you're not continuous, who knows? Maybe you'll attain your max. Maybe you won't attain your max. We're not sure, right? So you get the idea kind of what's the requirement. Now for this, the third example I wanted to do, here's this question here of why must f be defined on a closed interval? Right? And now here's a counterexample, and we actually kind of already gave it. Counterexample. What if you have a function like tangent or arctangent? It's not going to attain its max. Even though it's continuous, the function is continuous, but it's not enough to be continuous. You also need to be defined on a closed interval, right? But does not attain global extrema. Okay? So this is just kind of explaining the requirements. So remember, again, for the extreme value theorem, we have the requirement that f is continuous and f is defined on a closed interval. If these two are true, then we know that f attains an absolute max and an absolute min on the interval. Okay. So this is going to be helpful. So essentially, so far what we have is, let's see here. So far we have the extreme value theorem, which I'll just abbreviate as EVT. We have EVT, which tells us, which gives conditions under which a function attains extreme values. Okay. The next obvious question is, how do we find those extreme values? Right? So even if we know that the extreme values exist, how do we know how to find them? And this is where we come into play with Fermat's last theorem. So Fermat's last theorem says if a function has a local max or local min at a point, And so let's just highlight this. So if f has a local max or local min at C, and if f prime of C exists, then f prime of C is equal to 0. So this is going to help us out a lot, because what we can say is, let's look and see where f prime of C is equal to 0. That's going to be our first line of attack, if you will, in trying to figure out where we have extrema. Because if the function is differentiable there, and it's a local max or min, then the derivative is going to be equal to 0, right? In other words, if your derivative is not equal to 0, then you can't be a local max or local min. I hope that makes sense. Another thing is, as a result of Fermat's theorem, notice instead of writing f prime of C equals 0, we can write C is a critical point of the function f of x, right, of the function f. So this is another way to write this. Instead of writing f prime of C equals 0, another way to say it is to say that C is a critical point. Okay, so this kind of goes to, Pierre was hinting at this in class today. Pierre hinted at this. What's the connection? Here's the connection. Critical points, they show up in Famas Theorem. All right, so now let's look at an application of Famas Theorem. So here's an application. Of Famas Theorem. Consider this function f of x equals x minus 2 quantity squared plus 1. What does that look like? So it's going to be a parabola that is shifted to the right by 2 and up by 1. So it's going to look something like this. So this is x, this is y, this is f of x. Now, where does f have a local min? F has a local min at x equals 2, right? That's the vertex. Vertex is going to be the local min. This is where it occurs. What is the local min? The local min of f is 1, right? Because you look and you see, well, now what value is that? That's a 1. So f attains its local min at x equals 2. That's another way to write this. F has or f attains. Let's put this down. Okay, f has or f attains its local min at x equals 2. Okay, here's the deal. According to Fermat's theorem, right, if a function has a local max or local min at C, and if f prime of C exists, then f prime of C is equal to 0. So according to Fermat's theorem, f prime of, what is our C? 2. Right, this is where the local min occurs. F prime of 2 is equal to 0. Let's check. This is our f. So now f prime of x is equal to 2 times x minus 2. Okay? What is f prime of 2? F prime of 2 is going to be 2 times 2 minus 2. 2 times 0, 0. It checks out. So this is kind of showing us how we'll actually use Fermat's theorem. Okay. So true or false? If f has a local max at x equals c, then f prime is equal to c. True or false? This is false. Why is it false? Here's an example. The example is going to be, or here's a counterexample is what it's called. Here's our counterexample. Our counterexample is going to be, what about f of x equals absolute value of x minus 2? Now that looks like, it looks like an upside down v, right? So here's x, here's y. Now, doesn't f have a local max, or local min actually, at c equals 2? Yes, it does. Is f prime of 2 equal to 0? No, because f prime of 2 doesn't exist. Okay, so just because f has a local max or a local min at x equals c, that does not mean that f prime of c is equal to 0. What about the second true false? If f prime is equal to c, then f has a local max or local min at x equals c. True or false? False. This is false. Why? That's not what Famas Theorem says. Famas Theorem says if a function has a local max or local min, and if f prime exists, then f prime of c is equal to 0, right? It doesn't say if f prime of c equals 0, then there's a max. Here's an example. Here's a counterexample. Can you think of a function where f prime is equal to c, but f does not have a local max or a local min at c? What about f of x equals x cubed and c equals 0? F prime of 0 is equal to 0, but f does not have a local max or min occurring, that might be 2 R's, I don't know, at c equals 0. So this is called an inflection point, and we're going to learn about that later when we talk about the second derivative test. But, so just keep in mind what exactly our theorem is saying. It's saying that if, so let me put the zoom on it, if a function has a local max, and if the derivative exists, then the derivative is equal to 0. So just because the derivative equals to 0 doesn't mean that you've got a local max or a local min there, right? Something special is happening, but it's not necessarily a local max or a local min. Okay, so now all of this we're going to put together. Who cares, right? You're saying, who cares about this? Well, here's why we care. Because ultimately we now have a procedure for finding extrema of a continuous function on a closed interval, right? So we're putting together our extreme value theorem and Fermat's theorem, and we get this. Step 1 is going to be to find the critical values of f. Find the critical values of f. Don't forget endpoints, right? Remember, the critical values are going to be points where the derivative is equal to 0, points in the domain of your original function where the derivative is equal to 0, or the derivative is undefined, right? And we also have that we'll automatically get our endpoints because your derivative isn't going to be defined at the endpoint because you only have a left-hand or a right-hand limit. You don't have both. Now, the second thing we want to do is to find the values of f at its critical points. And then the last thing we do is you just look at all those values, and whichever is the highest, that is the extreme. That's the global max of your function. Whichever is the lowest, that's the global min of the function. Okay, so let's put this into practice. I've got these questions here we want to practice. Let's do the first one here. So these are an example, and our goal is to find extreme values of f on the given interval. Command copy, and let's paste. So we want to find extreme values of the function on the given interval, and our first function here is f of x equals 12 plus 4x minus x squared. So looking up at our first thing we need to do is find critical values of f. Okay, so if the first thing we need to do is find critical values, I'm going to look at the domain of f is all reals. So I can go straight to finding.
It's 2015.
Thank you. My derivative. F prime is going to be 4 minus 2x. Now, the derivative of the domain is all reals. So the only way I'm going to get some critical points from the taking the derivative is if I see when the derivative is equal to 0. So when is the derivative equal to 0? When 0 is equal to 4 minus 2x, which is when x equals 2. Okay? So what are my critical points? I'll have 2, I'll have 0, and I'll have 5. Because remember, don't forget your endpoints. Now, my step 2 is to find the values of f at its critical points. So this is step 1, was to get the critical points. Now step 2, we're going to find the values. So here's my critical point, and then here's the value of f at the critical point. So this is going to be a really short table because we've only got the numbers 0, 2, and 5 to consider. Now what is f of 0? F of 0 is going to be, go back to your original equation here, right? So it'll be 12 plus 4 times 0 minus 0 squared. So we get 12. What is for 2? We need f of 2, which is 12 plus 4 times 2 minus 2 squared. So that is 16. And then for 5, we need f of 5, which is 12 plus 4 times 5 minus 5 squared. So what is that? 12 plus 20 minus 25, 32 minus 25, 7. So that's equal to 7. So, aha! We're ready. I think I just did something. There we go. We are ready for step 3, which is the largest value from 2 is your absolute max, and the smallest value is your absolute min. So let's look here. What's my largest value? 16. So absolute max, which is the same thing as the global, of f on, what is it, 0 to 5, is 16. And note, this absolute max occurs at x equals 2. And the absolute min value of f on this domain, 0, 5, what is the absolute min? It is 7. And the absolute min occurs at x equals 5. All right, good job. Let's look at number 2 here. So let's look at this one. Copy. Oh, let me add a page afterwards. Add a page below. Okay, so this is number 2. And the first thing I want to do is find the critical values of f. So step 1, which is to find the critical values. Find my critical points. I like to call them CVs. Critical points. Find my critical points. Now, what's my domain? Domain of f is going to be all reals except x equals 0, right? Because I can't divide by 0, right? F of 0 is undefined. So when I list my critical points, I can't list 0 because 0 isn't in my domain to begin with. Now I'm ready to calculate what is f prime of x. This is going to be 1 minus, because I can write f of x as, let me show you here. So f of x is really equal to x plus x to the negative 1, right? So I just rewrote that 1 over x as x to the negative 1. And now f prime of x is easy to see because we can just use our power rule. And we get 1 minus x to the minus 2. So the same thing as 1 minus 1 over x squared, which we can write as x squared minus 1 over x squared. Now, let's see, what do we have? When is f prime equal to 0? For which x? And then the second thing is, when is f prime of x undefined? Even though x is in the domain. So for which x in the domain of f is f of x undefined? So this plus my endpoints are going to give me my critical points. So my critical points are going to come from when the derivative is equal to 0. They're going to come from the endpoints, and they're going to come from the points at which the derivative is undefined, although the points in the domain of f at which the derivative is undefined. So let's do this first one. When is f prime of x equal to 0? So let's do this one here. So f prime of x equals 0. That means x squared minus 1 over x squared is equal to 0. So that means x squared minus 1 is equal to 0. Remember, we talked about the only way this quotient is equal to 0 is if the numerator is equal to 0. And so that means that x is equal to plus or minus 1. So here I get x equals 1 and negative 1. Now, for which x in the domain of f is f prime of x undefined? Let's look here. When is this, where is f prime undefined? When the denominator here is equal to 0. So for x equals 0. But wait, we need for which x in the domain of f. And what do we say the domain is? All reals except 0. So we did not get any new candidates for critical points from investigating this question, right? Because the derivative is defined everywhere on the domain of our original function. And then lastly, for the endpoints, we'll have 0.2 and 4. Now, are we done? Almost, because these are candidates for our critical points, right? These are candidates, but look, what is our interval? 0.2, and then here's 4, right? And so like maybe here's 0. This is our domain. So the domain of interest of f of x is this interval here from 0.2 to 4. Now on this domain, 1, that's definitely in there, right? So 1, maybe that's here. So that's good. 0.2, that's here, that's good. 4, this is a valid one, so this is a critical point, critical point, critical point. What about negative 1? Negative 1 is back here. That is not in our domain. So negative 1 can't be a critical point because it's not in the domain of our original function. So our critical points are 0.2, 1, and 4. So the next thing we do, this is step 2. I believe there's somewhere right here. So step 2 is we need to figure out the values of our function at our critical points. So here are our critical points, and then here are the values of f of x at the critical point. We've got a critical point of, what do we say, 0.2, 1, and 4. So I need to know what is f of 0.2, what is f of 1, and what is f of 4. Now what is f of 0.2? it's going to be 0.2 plus 1 over 0.2, and that I believe is going to be 5.2. What is f of 1? 1 plus 1 over 1, which is going to be 2. And what is f of 4? 4 plus 1 over 4, which is 4.25. Now we're ready for step 3, which is to say that 5.2 is the absolute max of f of x on 0.2 to 4. It occurs at 0.2. The absolute min is going to be 2. 2 is the absolute min of f of x on 0.24. And it occurs, the absolute min, or also you can write absolute minimum value, it occurs when x equals 1. Okay? And that is the final answer. So I've got actually up here, these are these other practice problems. 3 is interesting, 4 is interesting, and 5 is interesting. I simply don't have the time. What I did on here, which I don't know, you might be able to zoom in and look at, is to see the critical points. What are the critical points for this function? This was for the third one. So we got the critical points here. You can kind of see how I worked it out. For the fourth one, down here, I worked out the critical points. And at this phase, you just put the critical points. Once you find the critical points, you just plug them back into your function and determine which is the largest and the smallest. And then for number 5, I did the critical points down here. So these are your critical points for number 5. Okay. So I'm not going to go over them in depth because I don't want the video to be longer than it is. I think I'm almost at 45 minutes. But you can, we'll definitely wrap back around to this concept and to practice this some more. I just really want to start related rates on Wednesday because I want to introduce it as possible. But we're definitely going to come back and visit finding your absolute max and absolute min. We're going to visit that again. So thank you for watching and good luck on the quiz on Wednesday.